Thank you very much.
Oh, you're welcome. I can hear you. Yes, welcome.
Thank you very much for the nice talk. And now I will go to our audience, to our colleagues, our students. So if you have any questions, I would like just here to say that Professor Saad was very kind with us. So he allows you to ask him allows you to ask questions even outside the topic of his talk. So, and in any language, English, Arabic, French. So please feel free to ask your questions. Please don't be shy. Amin? Sarah? Yeah, if you can just come here so we can hear you.
Thank you. So I first want to say it's a honor for me to talk with you. It's really.
I cannot hear you. Sorry, can you repeat the question again? Speak more loudly.
Do you hear me? Do you hear me?
Okay. Okay. Can you speak in English or in French, whatever you prefer?
Okay. First, I say that for me it's a high privilege. Sorry.
Yeah, go ahead. Yeah.
Okay. I say it's a honor for me to talk with you. I want to thank you first for your presentation.
Welcome.
For your it was I say more technical. Yeah. So I have a question. I have a question.
Okay.
On methods you talked about linear. A problem well, in reality, the truth is the problems are generally non-linear. Okay. So if there is let's say a chance to give a talk another time, maybe another time, to talk about non-linear problems.
Yes.
Okay.
Yeah. Actually, I'm very glad you asked that question because, in fact, one of the research topics I'm dealing with these days is exactly on nonlinear equations.
Nonlinear problems.
Yeah. So you're looking at, probably there is a very, and of course the word is typically nonlinear. The word is not.
Nonlinear.
Very often the word is nonlinear. So you have to find methods that work for nonlinear problems, and in particular. I mentioned earlier Newton's method, but there's more to it than just Newton. You have to find methods that work, that converge globally. There's a lot of work there. One of the methods that have been developed recently is called Anderson mixing, where this is something that was developed by physicists, where essentially you mix, you have a given previous iterates and then you try to find a combination very similar to what I talked about earlier when I talked about Krylov. So trying to find a combination of the previous iterates that give you a better approximate solution and that would converge faster. And that's very popular these days. There's a lot of research in this direction, a lot of papers.
Okay. And also you mentioned the SVR methods, the supervector machine methods.
Yes, right.
Yeah, I recently saw the SVR method, super vector regression methods.
Right, yeah.
So also, I want to, me and my colleagues and students, we want to have more, let's say, talks about this subject.
Yeah, so that one is actually not quite in my specialty. We had a paper many years ago where we talked about these, how all these problems come down to all the problems I mentioned, not necessarily SVM, but the other ones that you mentioned that have to do with optimizing, trying to get the best cut or whatever, they all can be formulated as a very simple problem, which is the following. How do you minimize the ratio of two traces, trace of a matrix divided by trace of another matrix, and then that leads to very interesting things. So we looked at that problem just as an alternative. But yes, SVM is very interesting topic. I don't think that there is as much research done in that area these days, but there are quotes available. There are lots of things that are out there that you could use. Yeah, so that's something. If you want to start it, get started in that area. Personally, I think there is something that could be done there to adapt the method to the new environment we have. So deep learning and so on. I think people have not looked at it. They just dismissed it. I think there should be more to be done there.
Okay. Thank you, sir.
You're welcome.
Okay. Any other questions? Please. Yes, Professor.
Professeur Saad, vous m'entendez?
Oui, bien sûr.
Alors, bien sûr, je vous remercie pour votre conférence. Et nos étudiants sont un peu timides, mais je vais essayer de les introduire dans le débat en parlant justement des outils mathématiques que vous utilisez. Parce que quand on voit le titre de votre conférence, on a l'impression que vous allez directement vers des mathématiques appliquées. Et quand on voit en profondeur ce que vous avez comme slide, ce que vous avez cité comme spécialité mathématique et options, donc vous avez commencé par parler d'analyse, d'espace fonctionnel, de topologie, de normes. Donc, il y a beaucoup d'outils d'analyse, de maths pure, je dirais, pour simplifier. Et puis, pour aller vers des mathématiques appliquées et de l'utilisation des mathématiques dans des domaines concrets. Et donc, nos étudiants et nous-mêmes au niveau de cette école, on est assez curieux de connaître la possibilité et l'utilisation des mathématiques dans des problèmes nouveaux, dans des problèmes et dans des issues donc innovantes et des problèmes qui ont besoin d'utilisation de mathématiques pures et d'outils de mathématiques pures. Alors tout ça pourquoi? Pour résumer, parce que comme je vous l'ai déjà dit, votre public s'est constitué majoritairement d'étudiants de classes préparatoires, donc de première année et deuxième année. Et donc, actuellement, ils suivent des matières de mathématiques fondamentales. Donc, essentiellement, il y a de l'analyse, il y a de l'algèbre, il y a des probabilités, des statistiques. En deuxième année, on commence avec un peu de mesure et de l'intégration, topologie. Et donc, ils commencent un petit peu à toucher un petit peu à l'application des maths. Bon, vous me direz aussi qu'il y a les statistiques, il y a les probabilités, où ils commencent dès la première année à toucher un petit peu aux data, aux données, etc., aux graphes, etc. Il va y avoir en troisième année aussi de la théorie des graphes, etc. Donc, les outils que vous avez cités dans votre conférence. Et donc, nous parler un petit peu de la nécessité d'avoir des bagages de mathématiques pures et comment justement les adapter et les appliquer pour des problèmes qui surgissent dans le quotidien et dans le secteur économique, industriel, etc. Et je vous remercie par avance.
D'accord.
Introduire nos étudiants.
Okay, so I will have to answer in English because my technical French leads me to a lot of hesitations. I could do it in French also, but anyway, yeah, that's a very, very good question. As a teacher in computer science, I struggle a little bit with that same issue because computer scientists don't have as a strong background in mathematics as you would find in math departments and so on. All of those tools you have mentioned are very, very important. I would say if you're interested in doing work later, doing research in anything that has to do with machine learning, then it's very easy. I'll tell you exactly what is used there. Statistics, linear algebra, optimization, and a lot of insight from mathematics. So if you have, for example, I mentioned earlier this issue of kernels, right? Using, when you do SVM, without kernels, SVM is useless because you have data where points are completely mixed. You cannot separate that with a plane. You have, so what you do is use kernels which is essentially which defines a different inner product, and that you can then analyze what's going on. But the kernels will separate the sets nicely, but you have to have that insight from mathematics to be able to use those tools. So I think, I mean, all of those areas you mentioned are kind of essential, even though they may not seem that way for the student at the time they're taking these classes, I think. So I think that, yeah, I mean, if you want to essentially train people in this new areas, it's really essential to have them good foundation, to have them get a good foundation in these areas. So I think that's what you're asking, right? It's really just talking about the importance of this field. So I think it would be important to have a curriculum that's dynamic. You'll probably want to change occasionally and give more importance to some areas than others. That is one thing, that system that's a little different in the US versus the France or Europe in general. In here, what happens is people adapt very often their curriculum, the curricula. So you take, there's a new field that's emerging out there, people will change. So we have to introduce this course, we have to introduce that course, we have to adapt that course. And then I think it's actually very important to do that.
Mr. Saad.
Oui. Yes.
I am Professor Ben Bashir Ma'ammar. Personally, I have a question about doing mathematics. Is it preferable to do theoretical mathematics or to do more practical? Is the proofs are very important in the curriculum of mathematics student? Personally, I have been at USTHB, Houari Boumediene University, and we have to deal with I mean French method for studying for schools, and I believe that from American and English books, they did not have the same method. They do not have the same approaches. I think that they have not the same technical words, definitions about things that we teach to our students now, because at the National High School of Mathematics we teach in English,
right?
And teaching in English, I think that it is not just a translation from French to English. I think so.
Okay, yeah. Well, you raise a very, very interesting question. I think I'm going to answer it now. So that's a very, very interesting question. The two systems are very different. And I mean, I don't know that I would say that you prefer one to the other, but it's very important to realize that you need to have a solid foundation in mathematics. And if you want to publish, for example, in this area, this indeed, people are interested in proofs and other things, but you also have to realize that there is a balance. You cannot just, the focus is not the theory. The focus should not be the theory. The focus is the methodology, the methods that you're using, the whatever problem you're solving, and the theory could be used to help you develop those methods or tools or algorithms. But I think in the French system, what happens is that there is too much emphasis on the first side, which is the proofs and the theoretical aspects of this. I think that has to be, and in my opinion, especially if you go to like engineering schools or something, then you really have to do that. In fact, if you look at, if you consider what is going on in French, the French educational system, the engineering schools don't have that problem because they know they have to solve problems, and they don't put as much emphasis on theory as in universities. Did I lose you? Or are you there?
No, I am here,
Okay,
Professor
okay.
Saad. Yeah.
Okay, yeah. So that I think it has to be. My impression is it cannot just translate, as you said, from textbooks or in French to English. You really take. I urge you to take books that are pedagogically well written, good. They emphasize both. For example, you see what I did just now with the talk. I gave demonstrations in MATLAB. I do that systematically in my teaching. That's always there. So you have to essentially be hands-on. People have to be applied, and they have to use the methods practically, and then the mathematical tools are there to support what they're doing. But it's not the goal. The goal is not just to prove something. The goal is to solve a problem.
Okay, thank you very much, Professor Saad.
Thank you, Professor Saad. We are back. So any other questions now? Yes, please. Can you come here? Yes.
So I have a question.
Sure.
It's concerning when developing new models to new situations we didn't encounter before. Does the mathematician have to, let's say, work with other specialists from maybe, I don't know, engineers from some other domains or other fields? So I guess that's how it happens. But can a mathematician gain knowledge enough to have a model that's, let's say, effective in a way where it could, let's say, link directly to the field that's not necessarily the mathematicians?
Yes.
So that was my question. Thank you.
Yeah. Thank you for the question. Yes, a very interesting question. I found it myself to be very motivating to have a collaboration with someone who is not from your field. For example, that project I mentioned earlier with physics. By the way, that collaboration lasted for 25 years, just to give you an idea. So it was a long time. We developed algorithms for algebraic problems, etc. So it gives you a different perspective, as you say. You learn some other things, and it's very, very important to have, a perspective that is just beyond just the solving that PDE or solving that thing. You have to say, wow, this is an interesting application. I want to solve this problem. I want to help in control. So if you see what I did myself in research, you'll find that I've done work in different areas. I kept jumping from one area to another, and I found it to be very insightful and motivating, and it gave me a lot of energy to this new area and tell them, yeah, you're doing something wrong here. You can do it differently. You can do it better. That kind of thing gives you sort of energy and insight, and I think that it really it does help to have a different perspective by working with other people in different areas.
Adding to the question, at what moment do we, let's say, know that that's the moment to collaborate? So when do we know that, let's say, we need more knowledge? So for example, we working on a small project that is inclusive, let's say, works in physics, but that's not very, let's say, developed physics that is, let's say, basic to some level. So at what point do we know that this project is actually interesting? And
okay.
Yes. So at what point do we know that we may make it, let's say, bigger and help?
Yes. I think I understand your question. That's a very good one as well. So yes, it is difficult sometimes to know whether the research you're undertaking is going to be interesting or valued by others, or would have an impact. I think one thing that is really important is whether or not your work would have an impact, and you can gauge that from knowing essentially looking at the number of people who cite your work or look at your work and so on. So that, but you have to go with what is interesting at the current time. It's not, I cannot, for example, suggest that you look at these methods that do things like eigenmap or manifold learning, because that was done a few years back. They were very nice, powerful tools, but the work was done already. So you have to look at what's being done currently, and that means really looking into current publications. You have to look at archive. Are you familiar with archive? I think you probably know what archive is. If you do research at some point, you will look at current publications, you look at archive, get the papers. They're all freely available, by the way. And then from there, you can start saying, oh, this is interesting. People are citing this work. It looks like an interesting topic you can work on, and then you can start doing looking at things you can do in that area. Oh, that's how I decide on topics for my students. You know, that's exactly. This you can do something better in this area. People are still interested in doing graph coarsening, for example. That's one of the topics we're looking at now. And how do you do it mathematically so that it does give you good results and so on. And then you can look at what's been done. You could compare with other papers, and you can start, doing the research and try to have something that does have an impact. It's not just publishing something; it's publishing something that has also a likelihood of having a good impact. That is what matters. You know, solve a problem, or make progress, very big progress in some specific area, no matter how narrow it is. But it's those kind of things could be more interesting than just trying to publish something out that will not interest other people or too many other people.
Thank you so much.
You're welcome.
Thank you so much, Professor Saad. Is there any other questions? Yes, please. Can you come?
Hello, assalamu alaikum. I want to ask a question for people that they are concerned in computer science and they want to learn more about computer science and deep learning. My question is, what's the best specialty do we have here that it will help more with this stuff? And do you recommend any other plan or any step it's better to do as people that are interested in computer science than mathematics?
Okay, yeah. So that's a good question. If you want to get into deep learning and things like that, I think it's actually not very, very difficult. Getting your hands into this area is facilitated by the availability of codes out there. So you can learn a lot from the internet. That's one thing that I could recommend. There's a very well-known and widely used package called PyTorch, which you can use. And with all the documentation that's out there on the web, it really doesn't take too much to learn about that. So if you want to just specifically work in deep learning, that is what you need. The first thing to do is to look at these codes that are available. And then you have to be aware of methods that are used. It's now essentially optimization type methods. Stochastic gradient is very easy to understand. There's nothing, it's very almost trivial to understand. But the things that are not easy are these heuristics that they put in to get the methods to converge, and there are a lot of things. But once you go beyond that, then it's not very complicated, because it's mostly the optimization, statistics, and I mentioned that earlier, numerical algebra, tensors, and things like that. So if you want to learn more about these things, you really have to get some documents, and there are documents that are freely available. Again, there's a PDF book by the people in I think in Montreal. Forgot the title of that book, that's freely available, that talks about deep learning. So you can learn from that book completely. So I mean, I'm repeating myself here, but there are a lot of documents out there you can learn by yourself. And then I have to say that my students did learn that way. They learned a lot of stuff by themselves. But it's different, because here if they need a class, they would just go to that class and watch. So they could have some they could learn from taking just one class or so, and not too many, but then that could help them a lot. You have to have at least one class if you want to really make progress quickly. But you can also learn entirely out of what's available out there.
Well, thank you so much. But my first part of the question was what's the specialty we can use as mathematicians that will help more with this type of stuff?
Yeah, it's typically statistics, optimization. There's not really as much in the way of deep math, high-level mathematics. It's really linear algebra. If you have a good background, for example, have these tensors, how the picture I showed you earlier, where you go from one layer to the next, those are tensors, they're parameters, and you want to optimize, find the best parameters. And so it's optimization, and there's a little bit of approximation theory, but it's really not much. You can completely ignore that, take it as a taken. But the main thing is statistics, linear algebra, a little bit of graph theory. When you have a graph neural networks, use that. That's basically it. Yeah, and then that's essentially it.
Well, thank you so much.
You're welcome.
Hello, greetings.
Sure.
Thank you for the lecture. I would like to say that I've liked it, even though it was a little bit intimidating. Now, being someone of less experience, I wanted to ask an expert in their domain, how does someone go about finding the right kind of problems, solving them? And how does someone find the links between the different learned concepts, even though at first or initially might not seem intuitive or obvious?
Second question was, how do you learn about the concepts?
I wanted to say, how can someone find the right kind of problems and how to solve them? And how can we find the links between the concepts we learn, even though it might seem unintuitive at first?
I see. Okay, yeah. I will answer the second question first. I think it's, once you have learned about the tools, when you do your own research, then it will come easily to you to see where a certain tool is used. It can be used, for example, whether it's in using these kernels or using the right optimization technique or whatever. So that part is not that complicated, I think. Which you have to know. You have to have that background in order to be able to use those techniques. On the first question, how do you identify the right problems to solve? And then for us, it's really dictated by, it's probably the context is different in Algeria and here. Here it's dictated by funding. When you get, there's a lot of money, for example, available for doing deep learning and for solving specific problems, then they encourage that area a little bit and they get funding for research. So that gives sort of a guide to what people would focus on. So that essentially one way in which the research is directed. The other one is just purely by looking at people students who are excited by something. All of a sudden they get excited by looking at solving a given problem, whether it's in deep learning or elsewhere, and they go in it. I mean, it's really once you get these lectures, maybe from outside, like this one perhaps, or even talks or even courses, then people will get interested in some specific topic all of a sudden, and they want to solve it, and then they get they engage in the research for that particular topic.
Thank you very much.
Welcome.
Any other questions? Any last question? Okay, I think. Yes, Amin? Yes. Yes.
Okay, hi. Okay, first.
Yes.
Yeah, thank you first for your informative presentation. And probably I will ask a question on behalf of all the students here. So we all know that you recently have awarded the John von Neumann Prize, and it's one of the most prestigious awards in mathematics. Mm-hmm. So my question here is, can you talk a little bit about it and about your work that leads you to get awarded of this prize. Just a little bit, if you want.
Okay. I have no problem with that. Yeah, sure. So yes, this prize is given every year to someone for two specific, essentially, reasons or for the award. And one of them is the have to have a contribution, have to make a contribution that had an impact in the field. And then the second one is that you have also, your work has also been given, essentially exposed to the scientific community in a good way. So, it's a pedagogical reason or for it. So those are the two things that are used for the selection. And also, I think I should also mention that this is not something where you get nominated. They just select someone like that. So I was very surprised by the award. I didn't expect it, essentially. So because there was no preparation or anything like that for it. So that's all I can say. I mean, it's very specific to applied mathematics, and it's specific to SIAM. So maybe people are confusing with some other awards, but this is something that's specific to applied mathematics. And yeah, SIAM awards it every year. I mean, the names of people who have been awarded this are quite impressive, I have to say. But that's the way it has been done in the past, and that's all I have to say about the award.
More question? Please. Don't be shy. Okay. So, Professor Saad, I have a question. Maybe the last one. Your journey in mathematics started from 40 or 50 years ago, and I believe you are an inspiration to me, to my young colleagues, and of course, to all our students. So, if you have tips or advices to our students at the National Higher School of Mathematics in a few words, if you want.
Oh, yes, sure. Yes, that's a very interesting question. Yeah. So I was in an environment that was very favorable, I have to say. I mean, in those days, we had a very strong University of Algiers was quite good at the time. I went to Grenoble. I was at the beginning of a good era in matrix computation and applied mathematics. So that's for sure. But what I would say to students who are in Algiers now, in Algeria in general, there are things that you can get quite easily. Remember, there was an Indian mathematician who came from very modest background, Ramanujan, if you remember, if you know the name, probably most of you will know. But he was able to make it because he was persistent. He was a genius. This man was essentially an ingenious. His inspiration was amazing. It was really, really amazing. So, but he was persistent, and then he contacted people abroad, and he was able to do something. And then eventually he was discovered by these English mathematicians. If you're working in Algeria, just get passionate about something. You need to get passionate about solving a problem. Go deep into it. Get the resources. You have, as I mentioned earlier, you have a lot of resources out there, and then get connections with people. Look at that's very important to be open to the world. Get connection. Here is my work, and then send it. If you also have to write nicely. I think something I cannot emphasize this enough. Write well. If your paper or your correspondence is bad, nobody will read it. Believe me. Okay, so you have to write nicely. Write in English or in French, whatever it is, but you have to write well. Your papers, your correspondence, that's very important. What I mean by well is just not the two things, of course, is the style and the orthogonal, the orthograph and not making mistakes and so on, but also the presentation of the ideas. you have, this is something that I recommend very highly to a school like yours, is to make sure that people will give talks. I do this in my group. I force the students to give talks twice a semester, though they learn, and then I criticize them if they don't do something well. The same thing for the paper, they have to learn. Now, it's really important to do that. Those things will really give you some, an advantage. It will put you in a better position. Be passionate, expose your ideas well, and be connected. I think those are the things that are very important.
Thank you very much for the valuable advice. So, if there are no more questions, I will invite Professor Dagri to say a few words.
Alors, Professeur Saad, on arrive à la fin. Au nom de tous, donc je vous remercie pour cette conférence à distance et j'espère que la prochaine conférence sera ici, in situ à l'école.
Avec plaisir. Ok.
On est très content d'avoir établi le contact avec vous. Inch'Allah, le contact hada yistamar et ce sera continu. N'hésitez pas aussi à nous contacter pour nous donner vos conseils, vos recommandations. Maintenant, quoi de plus beau de vous remercier. On va vous applaudir encore une fois.
Je vous remercie infiniment, professeur Moudari. Je suis très content d'avoir fait cette conférence et je suis à votre disposition si dans le futur pour faire d'autres conférences, Inch'Allah. D'accord. Je vous laisse. Merci encore une fois. Merci, je remercie beaucoup les étudiants qui ont posé des questions. C'est comme ça qu'il faut faire. Il faut être volontaire, il ne faut pas avoir peur des questions, etc. C'est bien.
Merci. Inch'Allah, une autre conférence et Inch'Allah, on vous verra bientôt à l'école.
Inch'Allah, d'accord. À la prochaine, Inch'Allah.
Merci, au revoir.
Au revoir à tous. Au revoir.
Salam.
Salam.